Welcome back. We will now look at some examples related to our concept on conditional probability and its application related to Bayes' theorem. We have already looked at how the probability triple allows us to construct a valid probability theory. So we have a sample space and event space defining a sigma algebra and then a probability measure defined over it. We also saw that in case the sample points are equiprobable, it becomes easy to calculate the probability as the favorable number of outcomes corresponding to an event A divided by the total number of outcomes. We also saw what a conditional probability is, that is, with an knowledge that a particular event B has occurred, we question what is the probability that an event A would occur with this additional or new knowledge. Then we defined the conditional probability of A given B as the fraction given by probability of A intersection B divided by probability of B. That is, with the knowledge that the B has occurred, the sample space reduces to the event B, and therefore the newer probability measure is nothing but the probability of A intersection B divided by probability of B. Then we will now look at an example that the conditional probabilities of A given B and B given A need not be the same. Let us look at an example where someone purchases a digital camera. So any customer who purchases a digital camera purchase along with that an optional memory card with 60% of the times, whereas a typical customer in addition to a camera purchases an extra battery with 40% of the time. 30% of the customer buy both the memory card as well as battery whenever they purchase the camera. So with this we can construct the events. Let A be the event that a memory card is purchased along with a camera. B be the event that a battery is purchased along with a camera. Then we can easily write P of A is equal to 0.6 because 60% of the customer do so. P of B, that is probability that the battery is purchased along with the camera, is 0.4 because 40% of the customer do so. Probability of both a memory card and a battery is purchased is P of A and B, the event A as well as B has occurred, or A intersection B, that is given as 30% or 0.30. Then given that a selected individual purchases an extra battery, okay, the probability that a memory card is also purchased, okay, what we are asking is probability of A given B, that is given by probability of A intersection B divided by P of B. So A intersection B is 0.3 and B is 0.4, so you get 0.75. okay. Similarly, if you look at the probability that a battery is purchased by a person, given that the person has bought a memory card along with the camera, is that is the event B given A, that is P of A intersection B divided by P of A, which again can be found out to be 0.3 divided by 0.6, that is 0.5. So you will now see that P of A given B is not equal to P of A, which is obvious. B given A is not equal to P of B, which will later on will make it to interpret that they are not independent events. But at this point we can easily note that A given B, P of A given B is not equal to P of B given A. They are two different bit of informations. We also looked at some results in the last lecture. Okay, the only thing is we can write, okay, intersection of three sets in this manner. P of A intersection B intersection C can be written as A intersection B intersection C, A given B intersection C into B given C into P of C. Okay. Then some more results also we wrote that conditional probability is a valid probability measure. For that we derived this as well as this. If E1 and E2 are disjoint events, then the conditional probability measures also add up. Then a simple example we can look at of how with the help of conditional probability we can solve certain problems. First, before we get into this problem, let us say if I am telling you that a fair coin is being tossed and you ask a question, what is the probability that in the third toss you see the head for the first time? Okay, it is easy to compute. It means that the first two tosses resulted in a tail, and only in the third toss for the first time you are looking at an head. So it is probability of tail into probability of tail into probability of head, which is 1 by 2 power 3 for a fair coin. So this is easy to compute, and this is a case where you conduct a sequence of trials or random experiments. They are independent. We will define more what we mean by independent events later, but roughly you would know what it is. The conduction of one experiment is not going to affect the outcomes of other experiment. In that sense they are independent. And not only that, the outcomes of the event, the probability of the events are the same and they do not change. The probability of occurrence of an head in the second toss is the same as the occurrence of head in the first toss, and so on. So in those cases it is easy to compute the quantities of interest to us. Okay, whereas here in this case we will look at a case where the successive random experiments depend on each other. Okay, and the events, the probability of occurrence of events themselves and therefore changes. So conditional probabilities will be of use in this case. Let's say we have 4 individuals. They all go to a blood bank for donating their blood. None of them know their blood type, but only thing it has been known or recorded is that one of them, only one out of those 4 individuals have the blood type O positive, and that is the one which is desired for a patient at that time point. So the nurse in the blood bank has to do the blood test, or what is called as typing, until they find the person having the O type, O plus type blood, and then take the blood from that person. So the probability that is of interest is, what is the probability that at least 3 individuals must be typed or tested to obtain the desired type, which is the O plus. Okay, so let us define the following events. B is an event that the first person type is not O plus, and let A be the event that the second person typed is not O plus. It is automatically, it has to be understood from the nature of the experiment that this will happen only when the first person is not of O plus. Then only we will go for the second experiment. Okay, so the question is at least 3 individuals must be typed, means the third individual or the fourth individual should have the desired blood type. Okay, so this is what we have to find out. Since we know that only one among the 4 potential donors have the desired blood type, then we know that probability that an arbitrary individual has a O plus type blood is 1 by 4, and therefore the probability that an arbitrary individual does not have the O plus type is 3 by 4, which helps us to find out the first probability of the first event. Probability of B is 3 by 4. But now for the second one, probability of A, to find out, we conduct the second experiment. But now, given that the first person is not of the type O plus, we are left with 3 individuals, and we know that one among the 3 individual has a blood of type O plus, and therefore the probability that that person, okay, when type do not have an O plus, is that is 2 by 3, because 2 by 3 is the probability that the second experiment will not help us to find the person of type O plus. Okay, now then probability that at least 3 individuals have to be typed is that the first 2 typed person are not O plus. Okay, that is A should also occur as well as B should also occur. So it is probability of A intersection B. So that is given by probability of A given B into probability of B. So probability of B is the probability that the first is not of O plus type, and given that the first is not of the desired blood type, what is the probability the second will also not be of the desired type? So it is the multiplication of these two probabilities, 2 by 3 and 3 by 4, that will give you this desired value. Okay, going further, we also saw that this result P of A1 intersection A2 intersection A3 of 3 events can be written as A3 given A1 intersection A2 and A2 given A1 and probability of A1. Okay, now if you use this for the previous example, if you ask a question, what is the probability that the third person on testing yields the desired blood type, which means that it is the probability that the third is of the desired type given that first isn't and second isn't, into the probability that second is not of the desired blood type given that the first isn't of the desired blood type into first isn't. Okay, so this and this probability we have already derived, so this is what we have to find. So here the third, having done testing for 2 people, there are 2 more that are left. Probability that the third person will yield the desired result is just 1 by 2. So it is 1 by 2 into 2 by 3 into 3 by 4, that will give you this. So conditional probabilities can be used in order to solve problems of this kind. We also saw how we can construct a partition of the sample space. A1, A2 to AK are all set of mutually exclusive, collectively exhaustive events, which allows us to write an event A, B, or even the probability measure of event B as the sum of the probability measures, okay, of AI intersection B for I varying from 1 to K. Okay, and this can also be written in this form. Okay, now let us look at a 2 simple example. Okay, so to quickly go through, a student has 3 different email accounts. 70% of message comes to account 1, 20% come to account 2, 10% come to account 3. Messages have got spams. For the first account, 1% of the messages are spam. For the account 2 and 3, 2% or 5% are spams. So what is the average number of spams the person will be looking at when the person uses all 3 accounts? So let A be the event that the message is from the account numbered I, for I varying from 1 to 3. Okay, so we will see that it is and B, let it be the one which is a message is a spam. Then you can easily see that P of A1 is 0.7 because 70% come from it. A2 is 0.2, A3 is 0.1, and P of B given A1, that is the message is spam given that it came from the account 1, is 0.01 because 1%, and so on. 2% boils down to B given A2 is 0.02 and so on. So the probability that an arbitrary message is a spam can be written as P of B is P of A given B1 into P of B1 and so on, which can be found out to be like this one. Similarly, if you are not given directly the probability measures of, say, let us say 3 events b1, b2, b3 can be easily constructed. This is again a very simple example. Let us say there are 3 machines b1, b2, b3 that make transistors, 1k transistors, okay, and then 80% of the okay, b1 produces 80%, okay, and then b2 produces 90% of the resistors, and so on, okay. So each hour b1 produces 3000 resistors, b2 produces 4000, b3 produces 3000, and so on. So a resistor, if you conduct, if it has a nominal value which is in the acceptable range, then it is accepted, okay. If its range, the value of the resistance should be plus or minus 50 ohm of 1k, then it is accepted. Then A be the event that the resistor has an value which is 50 ohm within the nominal value, that it is accepted, okay. So probability that you will accept a resistor given that it is from b1 is 0.8. Similarly, you have these things, and in order to construct P of A1, b1, b2, b3, we can easily find out that b1 produces 3000 resistors, b2 4000, b3 3000, they add up to 10,000. So their fractional contributions or the probabilities is nothing but 3000 by 10,000, and so on. Having computed individual probabilities, probability that an arbitrary resistor is acceptable, P of A, is A given b1 into P of b1, and so on. So which can again be found out like this one, okay. Then we looked at the Bayes theorem, okay, which allows us to compute a posteriori probabilities, okay. Okay, to this end we will consider an example. Let us say you have 2 urns. Urns are nothing but bags, okay, in which the first urn has got 2 white balls and 7 black balls, which means that the probability of picking a white ball from the first urn is 2 by 2 plus 7. The second contains 5 white balls and 6 black balls. Again, the probability of picking a white ball from the second one is 5 by 5 by 6. What we do is we toss a fair coin. If it results in an head, then we choose the first urn and pick up a ball. If it turns out to be a tail, then we choose the second urn and pick up a ball. So the probability that is of interest to us is what is the conditional probability that the outcome of the toss was head, given that the white ball was selected, okay. So we will do it as follows. We will write it as follows: probability that the outcome was an head given that a white ball was chosen is probability of H given W, okay. So probability of H given W can be written as probability of HW divided by W, that is it was head and we choose white, divided by probability of W. This again can be written as W given H into H divided by PW, okay. So again we can write P of W as sum of two such terms. One is W given H into P of H into W given H complement or tail into P of H complement, okay. So then we can plug in all of them. That is the probability that we choose that we get an head, and therefore we choose the first urn is 1 by 2, and given that we have chosen the first urn, it has got 2 white and 7 black, so the probability of getting a white is 2 by 2 by 7, okay. So this is the numerator. For the denominator we have this result, that is probability of getting a head and therefore choosing the first urn is half into 2 by 2 by 7 to get a white, or we could have gotten tail with a probability of and chosen the second urn and would have drawn a white ball with a probability 5 by 5 by 5 plus 6, which results in this one. Okay, now let's look at a last example. Let us assume that there is a rare disease and only 1 in 1000 adults are infected by it in a given population. So we can easily see that A1 be the event that the individual has a disease. Then P of A1 is 0.001, and let A2 be the event that the individual does not have the disease. Then it is 999 by 1000 or 0.999. What we do is, in order to test a person, we conduct a test, but the test is not very 100% sure. So if an individual actually has a disease, a positive result will occur with 99% of the time. That is, 1% of person having disease will go undetected. Whereas an individual without a disease, if you conduct a test, it will wrongly show a result of positive with 2% of the time, a normal. Okay, so if a randomly selected individual is tested and if the result is positive, we ask a question: what is the probability that the individual really has the disease? Okay, that is a posterior probabilities. Then the other conditional events that are given in the problem can be written. Let B be the event that the test results in a positive. B given A1. A1 is the individual having a disease. B given A1 is 0.99, because 99% of the time the test identifies the disease of a diseased person. Then B given A2, that a normal person being wrongly diagnosed, is 0.02. With all these, we can construct a tree diagram as follows, wherein we start here and we will put the event A1 here and A2 here. A1 is the event that the person has a disease, that is 0.001, does not have a disease is 0.999. Then here we will put the second outcomes of the conditional probabilities of what happens when a test is conducted. On a diseased person, if the test is conducted, it results in positive with 0.99, which is what is P1 A1 into P0.99. Okay, so if you multiply these two, you will get these values. P of A1 intersection B is this multiplied by this, and the test resulting in negative for a person having disease is 0.01. Similarly, for a person does not having a disease, a positive result comes with 2%. So A2 given B is this, and the fourth one. Now the question is, okay, what is the probability that of an arbitrary person being tested, the result will be positive? So that is nothing but the sum of these two probabilities. Because how do you get this one? We can see that P of B is sum of these two. What is B? B is equal to B intersection sample space. The sample space has got two partitions, A1, A2. Those having disease and those do not having disease. So B can be written as B intersection sample space, that is equal to B intersection A1 union A2. A1, A2 was a partition, mutually exclusive, collectively exhaustive set of events. So B can be written as union of A1 intersection B and A2 intersection B. Because they are also disjoint, their probabilities add up. So this is the P of B. Okay, so sum of these two is P of B, and we can always get P of A1 given B. Given that a person is tested positive, what is the probability that the person actually has disease? A1 given positive is A1 intersection B divided by P of B, that is equal to, you can see that A1 intersection B is this, divided by P of B is what is computed, that will give you 0.047. So this is an example of the usage of the Bayes theorem. Thank you. With this we will conclude this lecture.